matrix. Otherwise, it's called a system matrix. So, if you have a large geometry and a large model, and you hit compute, hit the compute button, then there are windows, monitoring windows, status windows, and you may find during that phase, it says assembling matrices. So then you know COMSOL is busy transforming the partial differential equation or combined partial differential equation in a lot of equations, basically extracting matrices. That's why it tells you assembling matrices. If you have very small models, it's going so flashy so quickly that you cannot see that term. But if you have a large model, you would see it. It takes a while. That's the first thing. At least this is the way COMSOL is working. The other thing, what was the name? Usually solid mechanic engineer. I also used it, but I forgot. ANSYS. I couldn't get out the name. ANSYS is a little bit different. But here it works. Special thing, it starts from the equation. That's why it's so flexible. You could put in your own equation and it would calculate this thing. In ANSYS, and also interesting to know the differences between the program packages, you can only use so-called elements. So if you want to do a solid mechanic calculation, you have to have solid mechanic elements. If you want to have a coupled problem, you need another elements. If you have a certain problem where no elements don't exist, you cannot solve it. Here you could. Most people don't, but you would have a chance to write the equation and COMSOL would generate the elements, so to speak. So that is definitely an advantage with COMSOL. Having in mind that KUL equal L actually stands for that, I condense it down again, short writing. K, you know it's a matrix, U is a vector of unknowns, and L is the load vector, also a vector, same dimension as this one. If you have this equation, how could you solve for the unknown? I mean, if this would be just a number, you would divide by K, so you would say U is L over K. Yeah? But because it's a matrix, you cannot do this way. What would you have to do to isolate U equals something? That means solving the equation.
1 over the determinant.
Yeah, it goes in the right direction. You have to write something here in front. What should you write here in front? You should write something here that somehow neutralizes this thing. Yeah? And you set something 1 over. Maybe you had this in mind. This is a matrix. If you would put in front of this what? A matrix. What matrix? If you put any matrix, doesn't help. But what matrix could help? This? No. But the inverse matrix, that some of you had in mind but did not want to share with us. If you multiply the inverse matrix with the matrix, what is the result? It's also a matrix, but it's a unity matrix. Unity matrix means if you multiply with a vector, it just is the vector, U. But of course, if you put here the inverse matrix, you should not forget to put it also here. Otherwise, there's a problem. So, what does it mean? If you think about this, what does it mean? One way to solve that equation, to solve the problem, is achieved by having the inverse matrix. And again, this is something the computer is perfect for. If you use MATLAB, and we will do it in an example, we actually do exactly this procedure. Let COMSOL calculate the system matrix, and then we use MATLAB to do the inverse, and then we just let MATLAB do the multiplication, and then you can solve in MATLAB the finite element problem. So this is one of the numerical methods how to solve the problem. Just calculate the inverse matrix. The finite element method provides that matrix during the phase of the sampling matrix, then it's available, and then it goes to the numeric method, and this is something also MATLAB could do, but COMSOL also can do. Inverse the matrix. So that's perfect. It's a very robust method. Why are we not finished with this? Basically, because you're probably limited by the size of the matrix you can inverse. You know, if it gets larger and larger and larger, it will not fit in your memory, and even if it fits in there, it takes more and more time to do that operation. So at a certain moment, it's not reasonable. If you get run out of memory, if you have this direct solution method, or it just takes too long. So then we need other methods, iterative methods. Maybe also share this with you at that moment. The standard way COMSOL decides for direct method, that's called direct method, is for 2D models. If you draw a geometry in 2D, then the corresponding matrices are usually, in most cases, small enough that the direct method can be used, means just let the matrix inverse. Then you have not a problem with conversion, because that is just an algorithm. It takes certain time. If you have enough memory, it works out. You may already guess, if you leave this, if you don't use the direct method, go to some iteration. Iteration means it has to go step by step toward it. That can go wrong. If you draw a 3D geometry and model 3D, then it automatically goes to some kind of iterative solution. That is another reason why the recommendation, strong recommendation, is start the modeling with 2D. Then you don't have conversion problem, it just goes straight. Even if the 2D is not the complete truth, you have to modify later, but you already get some idea what are the effects, where is a lot of mechanical stress, where it's not so much. And then later you switch to another method. That is, the general idea is to start simple. Do maybe not all physics impacts, maybe you start with one, solid mechanics, later you take temperature, and later you do current, and so on, so you make it more and more step by step. The tendency I observe, and I probably did myself when I was a beginner, people have the tendency to try to do everything first run, make a complicated geometry and do every possible detail physics in there, and then in many cases something goes wrong, and then it's difficult to find the problem. So it's better to start very simple. 2D is one of the key concepts, and then you later make it more complicated. Here I just put it in a short statement what I lengthily explained minutes ago. In order to give you a feeling, first-hand experience, how things are going, I like to invite you to do this modeling together with me. First I explain, and then we observe certain things here. In order to keep things simple, we first time do a 1D simulation. So this is a geometry, it's just a line with length L. So it's another exercise how to set up a model. We have to determine the geometry. In that case, we have to assign the length particularly. You will also see, if I do it practically, we can assign a cross-section even if we just simulate 1D. So how is that? That is just a parameter to calculate certain quantities. For example, if this is a wire, if there's a current, if you want to have a current density, you would need to divide that current by the cross-section. So with that parameter, you could calculate a current density in case you would need. So sometimes that is the case. What else do we need to do? When we finish the geometry, we have to assign material. So we have to provide that number for current flowing, the conductivity, the electric conductivity. Oh, by the way, the equation, should I switch back here? that equation, which I just discussed in general, would some of you have an idea what equation that is, what it describes, what could be the U in particular here? Heat conduction. Heat conduction. If you put for U the temperature, then that gives the temperature gradient. What is probably the C in that case? Material property? What material? Yeah, heat conductivity. Some number for the heat conductivity. If it's just a number, then this would be a linear equation. Could you imagine how that linear partial differential equation could become a nonlinear? COMSOL is taking care of this to investigate, take measures, how to handle, but just you would have to remember what we checked in that little exercise. So we have to check the coefficients in front, which are usually material parameters, can be constant. That is not a problem. They can depend on something, but only one thing is uncritical, the time. So if you would have a heat conductivity or electric conductivity which changes over time, because maybe drifting or something, would not make it nonlinear, still linear. But what is not allowed? The coefficient should not depend on the variable. So if you have a heat conductivity, which is not just a number, but itself depends on the temperature, then would be nonlinear. Same thing with electrical problems. If the conductivity, electric conductivity is just a constant, is linear, but that is in many cases true that the electric conductivity is temperature dependent. For increasing temperature can go higher or lower, NTC, PTC behavior. That makes it nonlinear. Okay, we assign a material and then we have to mesh it. The mesh, in the simplest case here, I distributed that knots equally spaced. Just to review our discussion about mesh, I'd like to point here to this slide we already discussed. At the mesh points where we put them, we determine where COMSOL calculates. You know, the 100 unknowns, in which region it calculates, the temperature or whatever we're looking for, the solution. And then the topic how to handle the regions in between, because we don't have an analytic solution, so we only know the solution here at that mesh points, how to handle this. The simplest way is linear. It's called the shape function, linear shape function. If you use higher order shape function quadratic, we discussed virtual mesh points. You don't see them, but this additional mesh point allows you to have a square function running through. You need one more point to calculate the curvature of the square. Why that was important? Because if you calculate, for example, the temperature, is nice, but you can derive from the temperature much more quantities by taking derivatives. So if you make derivatives and you have a linear function, you make a derivative, you get a number. If you make another derivative, you destroy everything. If you start with a square, you make a first derivative, you get a linear function, so you can at least make two derivatives without having zero. Just to review these conceptual things. Then, by assigning during the model wizard a certain physics interface, here it would be electric currents, COMSOL automatically sets up certain equations, equation of continuity, what is the source of current, it's written here, this is Ohm's law, it's such a constitutive equation, material law so to speak, and what is this? It's another example of a gradient. The gradient of the variable we're solving for, the dependent variable, the solution variable, how many volt, along the x direction. If you do the gradient here, it provides you the electric field. That is, you can take it as a definition. So these equations are set up. If you combine them, if you put that E in here and so on, you get this partial differential equation. That is the current density. Why it's zero here? It's zero here if there are no internal current sources. Of course, you can make boundary conditions, probably you should, otherwise it's boring. If you have only that wire and nothing connected, there will also be no current flow. So that is what the equation says here. Inside the wire, if there are no internal current sources, why there should be any, then it just means the source of the current is zero, no source. So you don't have to bother about this. What you have to bother are the boundary conditions. So what boundary conditions, if you want to let the current flow, one option would be to inject the current externally here, or to apply voltage would be another option. Here we just inject the current. Then of course the equation changes. If you have a current, we have a source which feeds the whole wire. Not to forget, if the current flows in here, what happens here, it has to flow out into ground. So these are the two electric boundary conditions we would apply. And then the question, the remaining task would be to solve for the electric potential along the wire. If we have the potential, we can calculate the electric field. The electric field is connected to the current density. Here in that case, actually, because the current density is set, we would be able to calculate the electric field, and then we could solve, if you know the electric field, for the potential. If I say we do, actually COMSOL is doing it, fortunately. You don't have to bother about it, but that's just the way it's doing it. But before it can do it, it has to reformulate the partial differential equation we just saw. It's written here into a set of linear equations. That happens if you had the compute button, then COMSOL will assemble the stiffness matrix and the load vector. And what we're going to do in that lab, we just do in a minute, we connect, that's another interesting thing which makes COMSOL even more powerful. You can connect it to MATLAB for certain purposes. So you can exchange data between MATLAB and COMSOL. For example, for optimization purpose, MATLAB has nice optimization routines, other possibilities. And we misuse, I mean, that's not a really use case for that LiveLink, it's called LiveLink, but just to make it transparent what's going on. So we build a model as described, we put it together, we exercise again how to set up a model, then we hit the compute button. Internally there will be the stiffness matrix, the load vector. We export it via the LiveLink to MATLAB. If you are in MATLAB, we can visualize the matrix, have a look how this matrix look like, and then we do something we already discussed. We try to inverse the matrix and then calculate things, so to speak, by hand, what COMSOL is doing for us. So, like I said, there should be a PDF describing the steps. I will click it here, so again, more options. You can just watch, you can join me clicking the model, you can do it by looking what I'm doing, and you can also open that PDF, which gives you step-by-step guidance. Maybe if you just watch, maybe you want to do it yourself afterwards, so you have the PDF. So again, strategic mistake. I should have started COMSOL. Which usually takes a while. Once it started, we just go to the wizard, model wizard, set up the model. What model? A 1D wire in which we want to run a current through. So what physics interface we use, you already know, the electric current interface. What is the dependent variable? The voltage or potential V. What type of study we should start with, or anyway should do here? Stationary, perfect. First stationary, then you may do other things like transient. But if you have a constant current flowing in, there's no reason to do any transient. If you would have a time-dependent current, then you might do a transient sim. So, in my case, it opened up. Anybody who wants to join and still waits for COMSOL needs a bit more time, or can I start? Here's the case. Then I just hit the model wizard, decide for the space dimension, in that case is 1D. Then we have to choose the electric current. It's an electric problem, open up. Electric fields and currents, open up. Electric current. So that is the correct mode. Oh, I know, because I did it several times, and you gain experience, and after some time in a certain field, you know what to use. That is the answer. And if you, maybe I should, if you don't know, then you call the COMSOL hotline. Then, no, that's the way it works. They give you a guidance for your problem. You should use this and this. I mean, of course you have to pay for that, but that's what all the companies are doing, particularly if they employ someone just starting with the topic. You know, it saves money. Instead of letting them researching for weeks what to do, so you pay a service fee, and then that's not unusual, because if you start, they give you some starting point. Okay, electric currents. That's why we put electric currents here. We call the COMSOL hotline. Electric is the dependent variable you see here, V, that's what we solve for. So nothing more, not multiphysics, just electric. Go to study. What study? Stationary. That's all. We can hit the done button, and now the model tree is pre-filled. Last time I saw people working here with that so-called ribbon. That's also perfect. I mentioned you can basically do the same thing working from left to right. For historical reason, that thing was just introduced later. I still use the model builder, but it's up to you what you. I always show you with the model builder, because usually I don't use this thing here. I prepared some global parameters. You know, in real world you might later think it to be useful to have them now here. I put them just in the beginning. That's a little bit artificial, and also to free you from typing them in. I should have put them in Moodle. I think I should put them in Moodle. Let me show you how they should be named. Lecture. Workflow, then part. Yeah, it should be called lab4 global parameter .text. This is some file you should find in Moodle if you want to click with me. It's possible to find, or?
Yes.
Okay. Then you download it somewhere where you can later on find it, and then I just open. It says German, the menu, the Windows menu, or öffnen, but I think you can handle it. Maybe I give some comments on what parameters I put here. Change this. I should be able to make it smaller, but I cannot do it. Anyway, then do it like this. Just a little explanation what we have here. There is a cross section of our 1D wire, A_R, the cross section of the resistor. It's pi r squared, so this is just the equation for calculating a area of a circle. Pi is a constant, COMSOL knows, that's why we can use it here. Now the next thing, the length of the wire. I have a formula used here. And I think I should explain what formula this is. Maybe some of you already recognize. Actually, what I use here is a kind of simple equation which allows you to calculate the resistance depending on the geometry, if it's a simple geometry like a cylinder or a block, which is the case here. We have a length and we have a cross section. Then we can calculate the resistance. It's the length divided by the cross section. That's the geometric part. It's so simple because the geometry is so simple. And then we have a material property part. If it's the conductivity, it would be 1 over conductivity. It could be the specific resistance, then you would have rho here. So you can use this very simple equation for the special case of such a simple geometry. And what I actually did here, I wanted to give or set the resistance as a certain value. Where did I put it?
I have more than you.
Yeah, that's the point. You know, I was wondering. That's also the reason I couldn't change. I have to lift it.
Yeah.
And now I also could change this dimensions here. You see, sometimes I forget what I did, but maybe not bad. So here I set the resistance to be 3 ohm. And the idea here is to calculate the length in such a way with a given cross-section and a given material parameter that the resistance becomes 3 ohm. I think I did this because I want to be able to calculate the overall voltage drop. So later I define a current to be 2 amp, which we run through the current to the resistor. So if this is our wire, which is actually 1D, and we run in here 2 amps, and the whole thing has 3 ohms, then you know from ohmic law U is R times I. 2 amps times 3 ohms should be 6 volt. To have there not crazy numbers, that's why I put it this way. I calculated the length according to that equation. I just resolved for a length of the resistance with the given sigma, the conductivity, a given radius for the wire. And here, what I do here, I calculate the current density. I run 2 amps through it, but I divide by the cross section. Why I do it? Because the program later wants to have a current density for configuring the current source, you know? That's why I already calculate it. So I hope it makes sense. These equations. So next, we have to care about the geometry. Fortunately, it's very simple. Huh? We just need to plot this 1D wire, so make a right click interval. This is something we can use here. So it starts at 0, not at 1 meter, but the length of the resistance is large, not J, large L underscore R. If I would have mistyped, if I screwed up and make LK, then it should indicate something is wrong. Maybe also just for your convenience, there is the option to browse Steuerung, control, space. No, why not? It should jump into the search mode. It's not doing, so I don't bother at the moment. Length underscore R seems to be correct. In case you can also look up. So let's build selected. So we have the wire. You see it has a strange length. Why? Because we made it to have 6 ohm along the wire. Now, we're done with geometry, very simple. Usually now we would have to configure the material. If we have a look in the physics interface for the equations, you basically may recognize the equations we just discussed. This is Ohm's law. That is continuity equation. What is the source of the current is some charge, and that is the relation between potential and electric field. So we only need one material parameter, which is the electric conductivity. So instead of defining a material here that sometimes people are doing, we explicitly define the material property. So you have to know where it's provided. It's electric current conservation, and if you click here, you see there is something conduction model. So it's the Ohmic law, and the parameter is taken from the material. So it would go here and look for the material, because there's no material defined, it would make a mistake, it wouldn't run. But if it's the only point where you have to give that material, you sometimes, and I just show it for that purpose, may change here from material to user defined. So you can explicitly provide the number here, it's not going to the material. Sometimes it's useful. So let me check again, Steuerung space, now it works. Global definitions, if we forgot how we named it. Where is it? Conductivity here, sigma r. Double click. And this root means that it's the internal structure. It always starts with root dot. You could kill root dot or delete dot kill to brutal. Don't killing here, delete. If you don't like it, just make it sigma r, like it's written up there. Okay, then we have provided the material information. And just in that case, you can ignore the little cross warning sign on the material, because we provide the material here. I'm not sure why COMSOL does not delete that warning, but that's the way it is. Okay, yeah, another topic I forgot to mention when I talked about the mesh. Maybe I just do it now here on the table instead of moving through all the slides again. We have our 1D wire, and we have mesh elements. So the question is, what is COMSOL doing, particular for the values in between? That depends if it uses first order shape functions or second order. If it's second order, it has some invisible in between mesh nodes where it would calculate values. So let's check what COMSOL is using. You can do this by going to the main physics node and scroll down a little bit. There's something called discretization. And here you find it's using quadratic shape function. That is standard for the reason we discussed. Then you can make two derivatives without ending up with everything zero. But in order to have it transparent, because we don't see that mesh elements, we want to control that we only get solutions at a point where we put mesh grids. We change here for that reason now from standard quadratic to linear. It's not very often that you show discretization. By the way, again, you cannot do this with ANSYS. You are fixed. Once you do it here, you can, every time you can change the element order. And again, why we do this? To have control that every mesh node we draw, we know it calculates, in that case, a voltage. What else? What else? We have to provide boundary conditions. So, how to provide boundary conditions? Go to the main node, make a right mouse, and then see what is available. So, in any case, we need a ground. We put this ground here is 0.1. So the current which flows in here gets synced, and we want to feed the thing with a current source. So right mouse click, normal current density. Normal means it just goes in straight. It's hard to imagine how it cannot go in straight with such a 1D structure. So we put it here, node 2, and that has to be configured a bit more in detail. You see here it's asking me for the current density. That's why I calculated the 2 amps into a current density divided by the cross section. So we have calculated up in the parameters. Let's see if we can browse. Steuerung space. Yes. I don't know why it didn't work with the other thing. So these are the 2 amps and this is the current density. Double click. Just to be very precise and clear with this, let's have a look again. We say we want to have 2 amps, and in order to calculate current density, divided the 2 amps by the cross section of the wire, which we calculated here. So that means now the physics is set up, not so difficult. Next thing is the mesh. So if we use a physics controlled mesh, let's see what it's doing. You see it's putting equal spaced mesh elements just to make the connection to what we discussed before. I try to convince you what COMSOL is doing, setting up a matrix. What would be the dimension of the matrix? I have to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Dimension would be 16 times 16. So we could do this, but I want to have it a bit more smaller to follow the elements in the matrix. So what option would we have to have less points? I mean, we could try to change it here from normal to coarse or so, but if we want to have more control, we go to the mesh, make a right mouse click, and use edge. That means it provides mesh along the edge. That probably wouldn't change so much, no. What is next? What could we do next to have control how many mesh elements we have here? Something you did last time, there was one meshing method which might be useful now if you want to control the number of elements. Some keyword.
Distribution?
Distribution, perfect, yes. It's very good if you already have these concepts available now. That's one of the reasons why we do these exercises, to get you familiar with the concepts. Right mouse click, distribution. And here we can explicitly name the number of elements. So I want to have 3 elements. We'll select it. So what are 3 elements? 1, 3, 4. 3 mesh elements means 4 mesh points. 4 values to be calculated means a 4 times 4 matrix. That's what we would expect. Next thing is run the simulation, go to study, compute, hit the compute button, and then what I told you here is the log and the progress monitoring. And this is a very small model, so you cannot see the step by when it samples matrices. You can see that it's calculating something. If you go up here, not here, but in the log. So you can see how much memories it's using and some things, but the point when it samples the matrix is also not permanently written here. You won't see. So in that case, it automatically provides a graph. We don't even have to do it custom made, but you would know how to do it. We exercised. This is the coordinate along the wire. This is the length of the wire, the end where we injected the current, and that is the electric potential. And you see, I mean, for that thing, we would not have to run a finite element simulation. We get 6 volt. 6 volt. Why 6 volt? Because we have 2 amps and 3 ohm resistance. 2 times 3 is 6 volt. So it's a very simple model. It's on purpose very simple. to follow the things in detail. So what is next? Now we make a connection with MATLAB. So that first of all is some technical thing we have to do. There is something, or should be something, COMSOL with MATLAB. So usually you start COMSOL 6.4, and there must be another icon, or if you go in the search thing there, COMSOL with MATLAB. So you should hit that button, and the console should be open. Not the console, but the console. Please try.
Yeah.
Then somehow it takes a while. This also some warning I might give you. The steps now sometimes very lengthy. Don't click around, then you can screw up with things. In my case, it took time to start MATLAB. If you do it first time, it might ask you for a username and a password. It's doing it.
Yeah.
Then I would like to ask you, type COMSOL, small COMSOL, for the username and the password. If you type COMSOL, you don't see it. So you do blind typing.
What's the password?
COMSOL. COMSOL, small COMSOL. So, and then if you type in the password which you provide now, then you have to wait, and hopefully MATLAB should open after some. It's doing it very good. Yeah, I tried to make sure, but last year sometimes it didn't work. So the MATLAB should be open, and then the next thing is I provided in Moodle. I hope I did. I think I did. I have to go. I have to see myself. It's an M file that is containing some MATLAB script, which is useful now for doing certain things. Let me go. I think I was already here to do it again. Lectures workflow. Workflow. Yeah, it's this file lab4 matlab.m. That should be somewhere in Moodle. And I would suggest, maybe that's the last thing, you download that matlab m file somewhere where you can find it later, and then we make a break, 10 minutes break. In that lab file, in that m file, there is a script I already mentioned, which we'll use to visualize the matrices and so on. You continue working, well, you're allowed to work, but otherwise we just do a 10 minutes break, like 3:40 would continue. Maybe we are quick and don't need all the time that we just finish earlier, but I like to continue at 10 minutes, or you prefer 15 minutes. No, I'm really up to whatever you want.
10 minutes.
10 minutes, okay. I have a chance to finish it now. If some of you guys who have to do the mini projects want to ask me something, I'm available. Now, but also after the lecture.
So my computer back up.